Thank you for coming to today's CAIDA talk. We have the honor to have Professor Hongyang Zhang, Assistant Professor at the University of Waterloo and the Beckley Institute for AI, to give us a presentation today. Professor Zhang received his PhD in 2019 from CMU, and he did a postdoc at TTI at Chicago, and he is the winner of NeurIPS 2018 Adversarial Vision Challenge, CVPR 2021 Security AI Challenge, Amazon Research Award, WAIC Unify Award, and so on. He also served as an area chair for NeurIPS SER, AI Stats, Triple AI, and abstract editor for DMLR. And he has lots of fantastic publications in top machine learning conferences and computer vision NLP conferences. Without further ado, let's give Professor Zhang a warm welcome for today's talk. Maybe before you officially start, if you have any question, feel free to raise your hand during the presentation. And also, if you are on Zoom, feel free to put your question in the chat box or raise your virtual hand.
Okay, thanks everyone for coming to my talk, and thanks Xiaoxiao for the great introduction. And we're honored to have the chance to give a talk here to introduce some of my recent work in my group. So today I'm going to discuss some new advances in safe, self-evolving, and efficient large language models. So this is the history of AI. So in the history around, we have experienced two AI winter around the 1970s and 1985. We experienced two AI winter, and right now we are in the third AI. So starting from demise AlphaGo, and then followed by Google's Transformer, BERT, and then followed by demise GPT, GPT-3, ChatGPT, GPT-4, and demise AlphaFold. And also recently, in the last week, we have seen OpenAI's DALL-E and also the Sora. So they have advanced the AI to lead us towards it. So that's why Microsoft researchers, they claim that in certain sense, they find that the GPT-4 is showing a spark of AGI. So here are some of the AGI characteristics. Although they are not a complete set, but they are very important subsets of AGI characteristics that I want to highlight today in this talk. So the first characteristic is that we want to make sure first the AGI should be safe. So that being said, we want to make sure that the generated content of the AGI or the AI should be harmless and helpful to the humans. So that's why OpenAI they launched this super alignment program to invite the world to build the safe AI. So this is the first characteristic. That's what we care about. And the second AGI characteristic I also want to mention is about the ability of self evolution. So we want to make sure that the AGI can know how to improve itself and how to use a tool. So this is very similar to the human because the way we can distinguish from animal is that we know how to improve ourselves and how to use the tool. So we also want the large language model, also the current AI, also has this ability of self-evolution. And the third characteristic I want to highlight is about the efficiency. We want the AGI, also the AI, to make decisions promptly and immediately. So this is pretty important for many real-world applications. For example, for the self-driving car, we want the car to make decisions immediately in order to avoid some traffic accidents. So this is all about efficiency. So in this talk, we will talk around these three characteristics: the safety, self-evolution, as well as the efficiency. So we mainly discuss the large language model today. And this cartoon, perhaps all of you have seen that before. And for the large language model training, typically we can see three phases. The first phase is unsupervised learning, or some people also call this pre-training. And then followed by the supervised fine-tuning to let the large language model to follow the human instruction. And then we also want to do the alignment. So this is called the ILHF. So reinforcement learning from the human feedback to let the large language model to output some safe content. But typically, people find that if you only do the pre-training phase or say this unsupervised learning phase, people view the large language model as a monster with several heads. And some of these heads, they might be benign, but some others, they might be harmful. So this is not what we want. So that's why we following the unsupervised learning, people also need to do the supervised fine-tuning to let the large language model to follow the human instruction. But that is still not good. So that's why we need to have this IRHF to pick up the cherry on the top to make sure that the output of the large language model is safe enough. So this is we want to pick up the safe sub-distribution from this monster. But you can imagine that to train a large language model is quite complicated. Not only we need the pre-training step, but we also need the supervised fine-tuning step and the IRHF step. And moreover, if you look at the supervised fine-tuning and IRHF, they not only takes a lot of computational resources, but also they require human annotators to label a lot of data, and this is very costly. And furthermore, especially for the IRHF, the training step is pretty unstable. So in order to get a good large language model, typically you require super rich engineering expertise. So the question is that, well, are they necessary? Is it possible that without the supervised fine-tuning and IRHF, we can still get a large language model to output some safe content? So that's where I come to the first part of the talk. I want to discuss the safe and also self-evolving large language model agents. And before we move on to the talk, let's first look at some prior works, how we do the large language model alignment. So this table shows a comparison between our work and some prior work. So the first work was given by Hongyang Zhang in OpenAI as early as 2022. So the method is IRHF. So this is perhaps one of the most famous methods in the large language model alignment. So for this method, they require, from the name we can imagine that they require IL, so definitely we require reinforcement learning. But as we mentioned, reinforcement learning may suffer from unstable treatment. So this requires rich engineering expertise. So, and also the HF here means human feedback. So definitely we also require costly human annotators to label the data. So this is also a drawback of the IRHF. And furthermore, if you look at IRHF, they also require supervised fine-tuning to let the human to write some instruction and let the large language model to follow this instruction. But the supervised fine-tuning also suffer from actual computational resources. And later on in the last year, Bai et al. From Anthropic, they proposed the IRAIF. So they try to replace the HF here with the AIF. So that means that we don't need the human feedback. We require the AI feedback. So definitely it doesn't require the human feedback because we replace all the things labeled by the human with the AI itself. But it still requires reinforcement learning because this is IL, and also it still requires supervised fine-tuning. So this also requires actual computational resources and data. And furthermore, in the NUIPS this year, Stanford University, they proposed a DPO method. This is also the winner best paper in NUIPS in the last year. And this method, they design new loss function. So they it doesn't require reinforcement learning because they design new loss function and they can fine-tune the model by an end-to-end way by backpropagation. So it doesn't require reinforcement learning, which suffer from unstable training. But the method still requires human feedback because they require the human to write the different outputs, which is better, which is worse. So they still require costly human annotations. And also they still require the supervised fine-tuning, require actual computational resources and data. And what I want to propose today, what I want to introduce today is a new method called Ring. This is also from our group, which we want to do post-training alignment, which doesn't require reinforcement learning, which doesn't require human feedback, and which doesn't require supervised fine-tuning. The hope is that we can avoids all these drawbacks in stable training, costly human annotations, and actual computational resource energy. So, but how we can do that? So this is a joint work with Yuhui Li and Chao Zhang from Peking University, and Fangyu Wei and Jingjing Zhao from Microsoft Research. So the full name of the method ring is called the rewindable auto-regressive inference. So you can imagine that from the name, you can see we want to call the rewind mechanism. So if once the large language model realizes the output is harmful, maybe they want to delete the current also. So here is a simple demo to give you a high-level idea about how this algorithm proceeds, and later we will also discuss some technical details. So let's say in this demo, let's say we are given a prompt, give me a guide for how to create fake news. And ring consists of 3 steps. So the first step is about the generation. So we let the large language model to generate something in an auto-regressive way. For example, given this prompt, we ask the large language model to output something, and let's see at this moment, the large language model outputs, sure, here is a guide. And in the next step, we ask the large language model itself to do the self-evaluation of the harmless level of the current output. And the scale is from -10 to 10. So let's say at this moment, the large language model gives a score minus. So -1 is a negative score. So that means that the large language model itself realizes the current output might be harmful. And then in the third step, we try to call the rewind mechanism to do this in a rewindable way. So because the large language model realizes the current output is negative, also is harmful, so it's trying to delete the current output. And then we just repeat these 3 steps. So let's say we do the first step again, the generation step, and in the next round, the large language model outputs IM, and we ask the large language model to do the self evaluation about the harmless level. And let's say in this step, the score is equal to 5. And positive 5 is a relatively good score. So the large language model try to keep the current what is generated in the last round. So let's say the output is IM. Then we repeat this procedure. Next round, we ask the large language model to continue generating the following sentence. So let's say it generates, I'm glad to have you, and definitely the score is -5. So this is harmful. So the score is negative. And because the score is negative, the large language model try to delete what is generated in the last round. Glad to have you. So still after this step, we still can only have IM as our current output. And we do this again and again, and hopefully we can output something harmless. For example, I'm sorry, but I can't provide assistance or guidance on creating fake news. So that is what we want. So this is okay.
And the evaluation. So is evaluating the self-evaluation. It's just evaluating sure.
It's just evaluate the generation in the current round. Sure, here is a guide.
So why is that?
So why is it?
Harmful?
Yeah, because so this is why it's generated.
Harmful only in the context of the query, otherwise it's not harmful.
No, give me a guide for how to create news. If the large language model output, sure, here is a guide. This must be harmful because it seems like in the following sentence, the large language model will help you to answer this question. But any answer to this question is
so the harmfulness is the query and
yes, including the query, the prompt. So if you look at the prompt and the generation in the last round,
if you have the query and IM.
Yeah, if you have the query and IM,
not harmful.
Yeah, not harmful, so the score is positive.
I mean, it's still harmful that you are trying to answer the question.
Yeah, at least it's uncertain at this moment. It's uncertain at this moment. So let's say the large language model is uncertain, but it's give a positive score. So let's say we keep the current answer, and let's see what the large language model will output as a later sequential way. So basically, if you want to do the self evaluation, you need to combine the prompt with the one is generated in the last row. Yes, this is a good. So this is just a simplified version, but let's look at a more complicated or say more technical version of the ring method. So let's say we are given a prompt, how to rob question mark. So this is the prompt. And what we want to do is that we want to build a tree according to the large language model. So let's say, given the prompt how to rob question mark, there are several possible ways to continue this prompt. Let's say to rob, for robbing and robbing is. So this is the next layer. And then follow the robbing is, there might be possible to output the illegal or separate. So definitely we hope the large language model can output robbing is illegal, because we hope the large language model to say robbing is illegal because this is harmless. But at this moment, suppose the large language model is not so well aligned. So perhaps with higher probability, the large language model will output robbing is acceptable. Let's say the probability is 0.7. And the large language model output robbing is illegal with the probability 0.3. So what we want to do is that we want to input both this tree, the large language model, as well as this probability into the ring method. And we want to get an adjusted probability. And we hope that after, as the output of this ring method, we want to get an adjusted probability. With higher probability, we want to say robbing is illegal. And with lower probability, we hope that the model can output robbing is acceptable. So this is what we want. So let's open up the black box in this ring method and see what will happen inside. So as of the first step, as we mentioned, we want to do the self-evaluation and attribute update. So let's say in the current round, we get how to rob question mark and to rob. So let's say the large language model first sample this branch, to rob branch. And then, as we mentioned, we want to do the self-evaluation. So we input how to rob question mark to rob into the large language model, and let the large language model to evaluate the harmless level of the current output. So this is the self-evaluation. And let's say the score is pretty low. So let's say this is the -1. So we want to set the value for the current node. So this is the current leaf node. The value b as -1. And also, in order to speed up the efficiency, let's say we also do the embedding for the to rob and do the embedding for the for robbing. And we compare the two vectors in the embedding space to see whether they are similar or not. Or let's say currently the similarity is 0.5. So we also want to set a value for the second branch as -0.5. So this is the self evaluation and attributes update step. And in the next step, we try to rewind because the current node, so this is our current node, and we find that the current node, the value is negative. So we want to rewind back to the root node, to the node in the above layer. So we get how to rob question. And in the third step, we ask the large language model to generate. So that being said, we need to go to the next layer. So let's see, because the first branch and the second branch, both of them have negative value. So perhaps we want to go to the third branch. So let's say the value is 0.2. So because this is the highest value in this layer, in the second layer. And then we do this again and again. And here I want to mention the value here, not only decided by the self-evaluation, but also decided by the large language model original probability, and also depends on how many times we have visited this node so far. So let's say the value is 0.2, this is the highest value. So in the third step, the large language model will get this branch, robbing this.
Yeah, there's one question from Zoom.
Yeah.
Raja, would you mind unmute yourself?
Yes, sure. Thank you so much. So quick question. So here the self-evaluation part, is the model that is generating at the very first place is the same model that evaluates the generated text?
Yes, they are the same model, So we require the large language model not only can generate, but also can do the self-reflection by itself. They are the same model, just a single large language model.
Okay, and how reliable is that actually? I mean, isn't it kind of like?
Later on we will discuss some experiments, and we find that for the pre-training model, such as the llama model, so llama model, the base model of llama itself is not very safe. But surprisingly, we find that they can realize they make a mistake. So let's say we input how to route question mark to route to the large language model to the base model of llama 2 model. We find that the score is already a negative score. So it seems like the large language model has the ability to realize it has make a mistake, but perhaps because it's make a decision too fast. So in the first generation, it outputs a harmful answer. But after it's because it has the ability to do the self evaluation, and the self evaluation accuracy is also very high. So we want to use this property or this ability to correct the mistake that is made in the last round.
Okay, thank you.
Thanks for the question.
How you collect those, question, or how you collect those
This
harmful questions or harmful texts?
No, this harmful text is generated by the large language model itself. It's not by human.
But those prompt questions.
The prompt, right?
Yeah, how to roll something like.
Yeah, this is from data sets. So later we will discuss the experiment. So this is a data set by Robin. So helpfulness and harmless data set. They have a lot of prompts, and they also have some ground truth. Also, we can also use GPT-4 as a to output the ground truth to see whether to evaluate whether the current answer is harmful or harmless or helpful and helpfulness. So these are from the data set. So the prompt is from the helpful and harmless data set. You can view that from you can find that from Robin data set. Any more questions?
Yeah. So why you didn't do this similarity?
Oh, so
How big is?
yeah, so we use this similarity because we are doing tree search. Basically, we are doing Monte Carlo tree search, and we want to speed up the efficiency, to search efficiency. So currently, we are at this node. So that being said, if we don't go to this node, we will have no chance to check whether this is harmful or harmless. So suppose currently we are at this node, and we know the similarity between these two nodes. That being said, we can also have the chance to check this node is harmful or harmless. So currently we are at this node, right?
Yeah.
And
you don't check for all.
But we didn't check the second. But we did.
Why don't you check for all the signals?
That will be slow because we want to also make sure that the efficiency, the search efficiency is also very good. So here
the order of the siblings counts. The order of the siblings counts.
Yeah, the same meaning.
Yeah, Robin is also.
Yeah, so that's why we can after checking this node, we know these two nodes, they are similar to each other, so we don't need to check this node anymore. And this
I understand that. Why don't you check also the other one? Robin is.
Because originally the large language model outputs some harmful answer. So the large language model didn't know that, and in the next round we check this node. In step 3 we check this node. Robin is. So the original frame means that this is the current node that we check.
Okay.
Thanks for the question. Any more questions?
Yeah, if you don't mind to remove that the discrepancy.
I don't think I have the can I didn't. You mean this one? Yeah, I didn't find it on my own screen.
Yeah, not on my side.
So this part, right?
Sure, here. Okay, cool. Thank you.
Yeah, so in the next round, let's say we repeat this three steps in a closed loop. So you can see that everything here is done by the large language model itself, but without any human intervention. And the large language model is doing the self-evolution or self-evolving. And we repeat these three steps until finally we hope to get to sample this node. And this node is good because Robin is illegal. This is what we want. So this is some more technical detail, and basically we are doing the Monte Carlo tree search on the token space, so that we hope to search for harmless answer. So this is what we do. And here is the experimental results. So we have so this is a helpfulness and harmless data set, and the red curve means this is the harmless rate, and the blue curve means this is the helpful rate, and the dashed line here means this is the vanilla method, vanilla auto-regressive method. And the solid line here is our method rate. So you can see, so basically you can imagine that the harmless rate and the helpful rate, in certain sense, they have a trade-off. So if you want to increase one, you will decrease another. But basically here in this experiment, the left figure is for the llama 1 model for different size from 7B, 13B, 30B, or 65B. And the right figure is for the llama 2 model, the 7 billion, 13 billion, and 70 billion. So for the left figure, you can see, with, for example, if we look at the 30 billion model, with the same helpful rate, we can improve the harmless rate by significantly. So there's a super significant improvement here. So this is the power of our method, or the ring method. And all the helpful rates and harmlessness rates is evaluated by the GPT-4 model. And so this is one example of self-evolving. So we use the large language model ability to do the self-evaluation, and then we use this ability to do the self-evolution to improve itself. And here is another example. This is a joint work with Yu from Tsinghua University and Feng Wei from Microsoft Research. So here in this task, we'll try to build a large language model as a to-use agent. So the task is to say, let's say we have an API pool, which has more than 16,000 APIs. So this is a huge pool. And let's say we have a user which has a query, and we want to fulfill the user's query to call the corresponding API. So what we do is that we input this API pool and the query into a method that we call any tool. So this is also the method that we develop. So this method serves as an API retriever to help us to select the best API that we should call. And then the method sends this API to the solver to execute this API and get a solution. And we also ask the large language model to record the history context, to record the history procedure. And according to this history procedure, we ask the large language model to do the self-reflection. And then this is another closed loop. We repeat this procedure until finally we hope that the large language model can help us select the best API from the pool to call to execute. So this is the task that we want to do. And in order to do this task, the experiments that we do is on the Rapid API dataset. So this is a library which consists of, as we mentioned, which consists of more than 16,000 APIs. And all the APIs are stored in a hierarchy architecture. So the first layer is about the category. You can see we have the finance, we have the sports, we have the category of music. And the second layer is about the tool. So within the sports, you can see we have the basketball, we have the ping pong ball, and so on and so forth. And within each tool, you have several APIs that you can call. So this is a structure of more than 16,000 APIs. So we want to build a tool, or say a large language model agent, to select the best API that we should call. So the way is that we have a user with a query, and we send this to the API. We want to build an API retriever. And because the data set itself is in a hierarchy architecture, so we also want to build the agent also as a hierarchy architecture. So the top layer is a meta agent. So the meta agent is can serve as a director or manager to control everything. The meta agent can control the category agent, where the category agent is responsible for selecting the best category from this data set. And as of the next layer, we have the tool agents. So all these agents, they are the GPT-4 model, for example. So the next layer is the tool agent, and the category agent can also control the tool agent. And the responsibility of the tool agent is to select the best tool from the pool. And then the tool agent can choose the best API that we should call and send it to the solver to execute these APIs. And then, according to whether the problem is solved or not, the large language model either save the solution or save the reasons as a text, as a file to store it. So this is like the memory ability of the large language. And then we send this record, the history record, into a self-reflection mechanism to ask the large language model to think according to this record whether the large language model can improve itself or not. So according to that, we want to go back to modify the meta agents, the category agents, as well as the tool agents. So here we get another closed loop. So you can see we can repeat all the procedure again and again until finally we hope that the large language model can get a good solution to solve to call the correct API that we should call. So here is the experiment on the self-reflection, the power of self-reflection, where the x-axis refers to the frequency of self-reflection, and the y-axis refers to the power, the pass rate, where the pass rate is given by the number of queries that can be solved divided by the total number of queries. So you can imagine that with the increase of you can see that with the increase of self-reflection, this is an increasing function, and roughly around 6 or 8, as small as 6 or 8 self-reflection rate, you can almost reach the topest level for the pass rate. So this is also quite efficient. So this is the performance we compare with the Llama. So this is a baseline method by Tsinghua University. And we also compare with the origin bar, which did not refer to the vanilla use of GPT-4, and the blue bar is our method. So you can see here, different bar means different data sets. So G1I is one data set, G1T is another data set, and G3I is another data set. So you can imagine that the improvement is at least 2 times and at most 8 times. So there's significant improvement here in terms of the pass rate. Yeah.
Oh, but very interesting study. I also have the question regarding your data sets. What kind of API did you consider, and how did you get the kind of like label like solved and also?
Yeah, we also so here we use this rapid API data sets, and also we have also, so this data set is not built by ourselves. So this is built by this paper, the 2LAM paper. And they also have the human annotator to label whether a problem is solved or not. So they have the ground truth.
Okay, cool. Thank you.
Thanks for the question. So this is the performance. And this is a more detailed comparison. So we compare with 2LAM. So this is a baseline method. And we also compare with GPT-4 and GPT 3.5 in different settings using different solver. So basically we can see GPT-4 is a little bit better than GPT 3.5 if we care about the same solver. And if we look at our method and the tool, so there's a significant improvement here. So we get the average as high as 58%, while the baseline method, the highest one is given by perhaps 33.5 or 38.9 average score. So we have a more than 30% improvement. So here is a demo. Basically, all what I show here is exactly copied from the proposal agent itself. So let's say we have a query. Can you recommend a book that highlights the importance of compassion towards animals? And also additionally provide me with a random word that show unity and accuracy. So here we have 2 queries. So one is to recommend a book, and another is to provide a random word. And as of the first step, we do the bootstrap API retriever. So we bootstrap the meta agents, the category agents, as well as two agents 1 and two agent 2. And then after this procedure, the 2 agent 1 and 2 agent 2 select here 6 candidates APIs that we want to call. Let's say search, find books, or search English, word infos, run and get a random word. And as of the next step, step, we try to bootstrap the solver. So the solver try to execute this API candidate and get a solution. Here is a book that might interest you, blah, blah, blah. However, due to the query limits, I could generate a random word. So this answer actually solved the first problem, but didn't solve the second query. Then we try to do the self-reflection. We try to ask the large language model to also consider whether it's do a good job or not. So that maybe at this moment, the large language model try to reboot to agent 1, to agent 2, and category agent. And also try to update the retrieve API. So let's say this one, they get a more precise API, the corrective API. Let's say find books, get multiple random words, and retrieve a response. And after calling the solver to execute these 3 APIs, so this is the answer, the final answer. So not only is recommend a book, let's say animal spy, but also it provides a random word. So it's successfully solved the problem. And all this exactly copied from the outputs of the agents that we built. So this we discussed 2 methods, the ring method and the any tool. Both of them built on the power of self-reflection of the large language model. But one of the drawbacks of the self-reflection is about the inference speed. So take a ring as an example. If we compare the time ratio between the inference time ratio between the ring method and vanilla inference, auto-regressive inference on different models, llama 30B, 65B, or say 70B, we can see that typically ring require roughly 4 times more time compared with the vanilla auto-regressive inference. So this is a drawback. So the next question we want to answer in this talk is that can we accelerate large language model decoding, make it even faster? And let's move on to the second part of the talk I want to mention. So it's about the lossless acceleration of large language model decoding. So here in this part of the talk, let's say we start from trying to accelerate the vanilla auto-regressive inference. So we will leave how to accelerate the ring, how to accelerate the any tool as our future work. But so let's say we firstly try to accelerate the vanilla use of large language model decoding. Because we want to accelerate the vanilla auto-regressive decoding, we need to firstly understand how we decode the large language model. So for example, let's say how is our prompt, or say our prefix, and we want to complete the sentence which follows this how. So we input this how into the embedding layer, and we get the embedding, how. And then we input this how into the transformer layer, we get a feature, or say representation vector, how. And then we input this how, or feed this how into the LM heads, this gives us an output distribution. And according to this distribution, we can do the sampling, and we can sample the next token. So let's say can. And then we try to go back to input this can into the bottom of the large language model, and we input it into the embedding, and we get the embedding of the second token. Let's say can. And we input this can into the transformer layers, we get the feature can. And we do this again and again, we get into the LM heads to the sampling, we get the next. So we do this again and again in a sequential way, and finally we will get a complete sentence. So this is how we do the auto-regressive decoding. But you can imagine that this is pretty slow because we are doing everything in a sequential way. So we need to do one after another one. So this is pretty slow. So every time we need to go through the whole neural network, the whole large language model to do the inference. So this is quite time consuming. And there's a method that we want to highlight today, which is also the key technique that we use. It's called the speculative sampling. So this framework has 2 modes. One is the draft mode. So let's say we have the prompt how, and we have a tiny model. And in the draft mode, we input this prefix or say prompt into the tiny model, and we get the output distribution of the tiny model. Let's say it's called the Q how. And then we this is the output distribution. We can do the sampling. We get the next token, can. So this can might be consistent with the large language model, or say might not be consistent with the large language model, depending on the quality of this tiny model. So we get the next token. We input the can into the tiny model again. We get the output distribution Q can, and we do the sampling. and we get the next token, I. So we also do this in a sequential. But this is pretty fast because it's a tiny model. We do not need to do a lot of computational calculation here. So this is pretty fast, even though this is still a sequential decoding. So this is a draft mode. And second mode is the check mode. So let's see how can I, this is a sentence that is guessed by the tiny model. And then we can, because the large language, so this is, let's see the blue layers, they are the ultra large language model that we want to accelerate. Because the ultra large language model, at this moment, they can see a complete sentence, although this sentence might not be accurate, but the large language model can see the complete sentence. So they can check all the tokens in parallel. So we have how can I, we input them into the embedding layer in parallel, we get the embedding, how, can, and we input them into a transformer layer, we get the how, can, fi in parallel. And finally, after going through the LM head, we get the output probability of the ultra large language model. Let's say P how, P can, and Pi. And because in the last round, in the draft mode, we have already get the probability of this tiny model. Let's say Q how, Q can, Qi. So you can compare P how, P can, Pi with Q how, Q can, Qi to see whether the guess from the tiny model is accurate or not. So you can decide whether to accept the drafted token or not. So this is the check mode. And after this check, you can guarantee that the outputs will be the same. The output text distribution will be the same. Because you use a tiny model to do the draft, and you use this ultra large language model to do the check. And if it's reject, you can just delete this token and just keep the current token that's which is correct. But the next issue is how can we choose a tiny model to do the draft? So let's first look at how existing works. Choose the draft model. So typically, let's say you have a llama chess 17 billion model, you want to accelerate. So in order to choose a small model to draft, people typically use a tiny model in the same series. So for example, this is a llama chess model. So you use a llama chess 7 billion model to do the draft for the llama chess 70 billion. But if you suppose you have another model, let's say the llama model, but that is a base model. Let's say this is a non-chain model, but it's still quite small, 7 billion model. So if you use this model to draft the llama chess 70 billion model, typically you will see negative improvement. So it will be even slower because you can imagine that the acceptance rate will be pretty low. So most times the draft is not accurate. And also another problem is that what if we want to accelerate the llama chess 7 billion model? So this already is the smallest model in the same family. We don't have even smaller models than the 7 billion model within the llama family. So some people may say we can use a tiny llama. So this is another model. But the issue is that tiny llama has no chat version. And also some people may say you can pre-train another model from scratch. Let's say you train a llama chess 1 billion model from scratch, but you can imagine that will be super costly. So we want to firstly save the cost, and also we want to also solve this problem. Let's say we want to accelerate a very tiny model. How can we do that? So here is our intuition. So let's say we have a how can I, and we input them into the embedding. We get the embedding vectors in how, can, and if we look at the evolution path over the time within this layer, within this bottom layer, so from how to can to what is the evaluation path? You can see that typically you will see that the dynamic will be very complicated. So that being said, if you want to describe the evolution path over time in the bottom layer, you require super large language model or super large model to capture this evolution path. However, if you look at the top layer, so you have the how, can, you input them into the transformer layer, you get a feature. And if you look at the evolution path in the top layer, f how, f can, fi how, f how become f10 and how f10 become fi, you can see that the dynamic will be very simple. So that being said, you only need a very tiny model to predict the evolution path here in the top layer. So this is our intuition. So we want to, our method is built upon this intuition. We call this method Eagle, and this is also a joint work with Yu Hui, Li, and Chao Zhang from Peking University and Fang Wei from Microsoft. So what we do is that we try to predict, we try to do the next feature prediction rather than the next token prediction. So let's say we have the prompt called Can9. So this is our prompt. And we input, and the blue layers, they are the ultra large language model. And we freeze the parameters here. So we input the Can9 into the embedding layer, we get the embedding. And we input this embedding to the transformer layer, we get the feature, f-how, f10, f5. And what we want to do is that we want to train a tiny transformer head, which we want to do the next feature prediction. So we want to input the f-how, f10, f5, input them into the tiny transformer head and try to predict the next feature. Let's say f-help. And with f-help, you can definitely input them into the frozen language model head and get the output distribution. And after sampling, you can get the next token, let's say u. And as of the next step, you have the f-help as well as the previous features, f-how, f10, fi. So you also input this all these 4 feature vectors into the tiny transformer head, and you try to predict the next feature. So let's say you get the next feature as fu, and you input them into the LM head. After the sampling, you get the next token, the question mark. So you do this again and again until finally you will get the end token, us, and that's where you complete the whole sentence. So that is how you do the draft. So here's a comparison about the size of the tiny model and the ultra large language model. So if the ultra large language model is 7 billion model, the number parameter in the draft, this tiny transformer head is as small as 0.24 billion. So you can see the ratio is roughly 3%. And you can even make the large language model even larger, 13 billion, 33 billion, or 70 billion. But the number of parameters in the draft model is no larger than the 1 billion. So typically the ratio is less than 3%. So the tiny model is very tiny.
We have one question from Zoom. So could you please explain why the draft track model is faster? From Rui's understanding, the larger model still need to do all the computations and auto-regression in order to accept or reject the draft.
Yes, exactly. That's a very good question. So firstly, the draft model is pretty fast. I think you can see that because the model itself is very tiny. And about the check model, because you have already seen the complete sentence, so you have all the tokens ready, and you can input them in parallel into the embedding layer. So everything is computed in a parallel way. So you don't need to. This check mode is not a sequential way. It's in parallel way. So that's why we can also do everything faster. Although you can imagine that the computational the amount of computation here will be higher than the normal auto-regressive calculation, but because everything can be done in parallel, so this check mode can also be pretty fast.
So let me see. Okay, thank you.
Any more questions?
Maybe I have another question.
Sure.
Just regarding this parallel input. Have you heard about the recent architecture for Mamba?
Yeah, Mamba is different. It's better use the transformer layer, and also in order to train the Mamba, you need to train from scratch. But here we want to say we freeze the ultra large language model, but we only want to accelerate it. So is that possible? We only plug in and train a very tiny model, which we can accelerate the ultra large language model. That's our task. That is our goal.
Thank you.
So this is how we do the draft. And here is the performance. We compare with the vanilla speculative sampling, denoted by this light blue bar, and also we compare with two state-of-the-art speculative sampling implementation called Medusa and Look Ahead. And here the y-axis refers to the speed up ratio, So you can imagine the blue bar is our method ego. So you can see that compared with all the previous methods, there's a significant improvement here, roughly 3 times faster than the vanilla auto-regressive inference. For different model, Vicuna model, and also the llama chat model. So here we can see ego is 3 times faster than vanilla decoding, and typically 1.6 faster than the previous best known results, the Medusa method, and 2 times faster than the local head method. So to the best of my knowledge, ego is the fastest inference method within the family of speculative sampling. And also it can probably maintain the text distribution. And most importantly, it can be trainable and testable over some cheap GPUs such as the RTX 3090 GPUs within only 1 or 2 days. So here is some video about we are given the same prompts for different methods, and we want to use the large language model to output something. And we compare with some baseline methods. The top left corner is the vanilla decoding. The top right corner is the Medusa, one of the previous best known results. And look ahead is at the top left, at the bottom left corner, and ego is our method. So you can see here in terms of speed rate, the speed, ego is roughly 30 tokens per second, while the baseline method is roughly 8 tokens per second. So this is roughly 3 times faster. And also it's even faster than Medusa and faster than the local head. So Medusa and local head is in the middle of the vanilla method and the ego method. Okay, so we have 5 more minutes, so let me do the conclusion. So in this talk, we discussed 3 works. The first is the rewindable auto-regressive inference, in short, RIN. And we want to build a method to, we build a method based on the ability of self-improving of the large language model. And this is a post-training alignment. So it doesn't require any alignment data or the parameter updates. So this is pretty cheap. And on the llama 30 billion model, we can improve the harmless rates from 82 to 97 without hurting any helpful rates. So this is also good. And we also discussed the second work we discussed is large language model agents, large language model tool agents. So it's called any tool. So it's a self-reflective hierarchy multi-agent system. And in terms of pass rates, it's even 2 times or 8 times better than the vanilla GPT-4 function calling ability. And because the limitation of the 2 methods is about the speed, so we also want to find a way to accelerate the large language model decoding. So in the third project, we discussed the ego. So this is a new method which gets 3 times faster than the vanilla decoding. And also it can probably maintain text distribution because we have the check mode. So that's why we can also achieve lossless acceleration. And more importantly, this is a computational friendly. It can be trainable. The tiny heads can be trainable and also testable on some cheap GPU. So even the GPU pool can afford this method. So that's all I want to highlight today. And thank you so much for your attention. And also I list all the QR codes for all these 3 projects here. And thanks.
I believe we still have time to take a few more questions here. So thank you, Professor Zhang, for the great talk. If you have any question, feel free to ask. Or if you have any question, if you're on Zoom, feel free to unmute yourself.
Yeah. Thanks for the talk. Just a basic question. What information do you provide to RAIN such that the score of the harmfulness changes over?
Which project?
RAIN.
RAIN.
Yeah.
The confidence. We didn't provide the confidence interval. So this is just the helpful rate. I think you are asking this slide, right?
No, can you go one before?
This one?
Yeah, here. So what information are you providing over the iterations such that the score is changing?
Oh, this score is evaluated by the large language model. This so the large language model outputs this.
Yeah, but what is changing over the iterations?
What's the change over time?
Across the iterations.
Oh, you mean the score?
Yeah.
In terms of experiments. So we show that in the paper. Maybe so I didn't have a backup slide for that. So we show that in the paper. Okay, this is in the ablation study section.
Okay.
Thanks.
Thank you.
Yes.
May I ask a question towards the second project?
Yes.
And I think it's important to categorize those API
Yeah.
to achieve improvement. So did you, how you categorize them?
Yeah, so here we use an existing library called Rapid API, and they have already done that for us.
Oh,
But I think this is a good question. So imagine that for the future we have another task. I think it's also very important to let the large language model has the ability to decompose a very complicated task into several small tasks to do it. So basically here we do this by human hands, but as of the future work, we may try to consider how to decompose a bigger task into small tasks automatically by the ability of large language model itself.
Any more questions?
On this, any tool, the feedback, whether it's correct or not, is coming from another language model?
No, everything is a single large language model, but you can imagine we copy the large language model several times. So let's say we use a GPT-4 serve as a meta agent and also serve as a category agent, but also serve as a two agents, but they are independent.
No, but then you have the solution.
And we have a solution. Yes, we have a solution.
You get this feedback.
Yeah, this is also evaluated by the large language model itself, not by the human.
How accurate is that?
We also show that in the paper. It's pretty accurate. So we do the ablation study here. It's pretty roughly 70 or 80% accurate because the GPT-4 is super powerful. So here we use
so when the feedback is wrong, let's assume that the solution was correct, but the language model says it's not correct, and it goes into self-reflection on wrong feedback.
Yeah, that's why we also can see it's not perfect. The accuracy is not perfect. We still have some failure case. So and this failure case perhaps because the large language model evaluation is not accurate. Perhaps perhaps other thing, or say perhaps because the retriever is not good, the solver is not good, or perhaps because the self-reflection is not good, or everything is good. So that's why we can see some failure case. This is not 100%.
I have some detailed problem for self-reflection. How do you do self-reflection? I see a paper and just I think concatenate some environment feedback to a prompt and then prompt to be again.
You mean for the any tool or say?
Any tool, yeah.
Yeah, so yeah, definitely, yeah, you are right. We concatenate the prompt with the solution and we input them into the large language model to see, and use the self-reflection ability of large language model to see whether there is any room to improve itself or not.
Did you try self-criticism, like ask GPT to give some advice to improve?
Yeah, I think they are doing the same thing. So here, we also use a GPT. So this, all this project, all the agents, they are GPT-4. And here, the self-reflection is also GPT-4.
Another question is, is there any growing problem in this case? I think in this benchmark, like every combination of API is legal action. So how about another benchmark like some?
Yeah, that will be one of our future work. So we also, so here you can see in this, the ATB is the new data set that we collect called any tool benchmark. We also collect more than 400 instruction queries, and this is also a new benchmark. So I think benchmarking the ability of large language model to use a tool is very important.
I mean, like when the output of GPT is not a legal action, how to solve this by self-reflection?
What is the illegal mean?
I mean, like you will output some action it's not achievable.
Oh, here, yeah. So for this ATB, we also filter all APIs so that all the queries achievable, is solvable. We want to guarantee that all the problem is solvable in this ATB benchmark. By human, we use a human label to filter so that we guarantee that all the problem is solvable.
Do you try to like do some self-improvement to put more skill in your API?
So 16,000 API is the largest API pool that we can achieve right now. So currently there's no larger library. So if people build that.
I mean, do you like do you think Voyager is a very similar paper, and they try to solve Minecraft game?
And which paper?
Voyager. Yes, but
yeah, maybe we can discuss.
Oh yes.
Yeah, so just for the sake of time, we have another meeting in this room, so we have to close today's talk. And thank Professor Zhang again. We also appreciate CAIDA and support and facilitate this meeting. And thank you again for coming here. Please enjoy the food, coffee over there.
Thank you everyone.